So now that we know the rules of probability, let's talk about how we find probability. Probability is that each outcome has the same probability of occurring, or all of our outcomes are equally likely. So if we think about flipping that coin, we want to make sure that the coin is equally likely to land on heads as it is on tails. Think about flipping a fair coin or rolling a pair of fair dice. That's what makes it fair, is that you are equally likely every time you flip a coin or every time you roll a dice, you are equally likely to get some of the outcomes. Now, our formula that we're looking at here says that we have the probability of an event E is equal to the number of ways E can occur divided by the number of possible outcomes. There's a few things I want to highlight in this formula. First, the fact that capital P is going to stand for probability. Be sure that you take note that capital P stands for probability because we're going to encounter 3 more P's through the rest of this course. So we're looking at the probability of some event, and then we count up the number of ways that that event could occur out of all the possible outcomes. If we look back at a problem that we worked previously where we were deciding the probability or the likelihood of getting a head with an even number, you can see how that formula looks in this way. First, we're starting with our probability statement, which is a capital P. Inside of the parentheses is the event we are looking for, the head and an even. And then over here, our 3, which is in the numerator of our fraction, that's us counting up the number of ways the event, the head and the even, could occur. And then, of course, the 12 are all the possible outcomes for flipping a coin and rolling a die. So let's look at an example then that's going to practice this again. Here we have a set of dice, 6-sided dice that we want to roll, and we want to calculate some probabilities based on the rolling of those dice. Now you'll notice that I've already given you the outcome space here. So what you see on the screen are all of the pairs of combinations that can occur when you roll a pair of dice. And if you count them up, you'll see that there's 36 different combinations of rolling the dice. Now, let me point out one thing that students generally get confused on. Students will look at this dice roll of a 2 and a 1 and think it's the same exact dice roll as the 1 and the 2. Now, although I can roll those two different scenarios that you're looking at there, and they're both going to add up to the number 3, they're actually not the same roll, and that becomes clear if I just color and think of the dice as being colored. If the first time I roll the yellow dice, I roll a 2, but the second time or another time I roll the yellow dice, and I get a 1, those are not the same rolls. So what we're looking at here are 36 different unique combinations of rolling these two dice. So the question we want to first answer is find the probability of rolling a 7, and then we're going to do this both empirically and theoretically. I'll explain what those two terms are in just a moment. So I want to know, what's the probability, capital P, of rolling a 7? That's the event I'm looking for. Well, how many different outcomes, what are all of the possible outcomes that can occur from rolling 2 dice? 36 possible outcomes go in the denominator. Now I need to figure out how many ways can I have my event occur. How many different ways can we roll a 7? Well, I have a 6 and a 1, 5 and a 2, 4 and a 3, and then you can see I have the same 3 and 4, 2 and 5, 1 and 6. That tells me that there are 6 different ways, 6 different combinations to get a sum of 7 when I roll it from 2 dice. So 6 out of 36. When I divide that and find my decimal value is 0.0167. This method of finding probability using a math formula is what we call the theoretical method. Theoretical or classical method. So if you think about math being theory, that's where we're getting this theoretical method from. Now, the second thing to this problem says, I want to figure out what my probability is of rolling a 7, but I want to do it using an empirical method. So the probability again of rolling a 7. When I do empirical, I'm actually performing an experiment, which is why it's telling me how many times I'm going to repeat my experiment, a total of 10 times. We can do this using a simulation since we're looking at this video, and that's what we're going to do. We're going to simulate rolling a pair of dice 10 times and count up how many times did I get my dice to add up to be a 10. So I'm back in StatCrunch, and I'm going to actually use one of the applets similar to what we've looked at before. I've already got this set up so that we're looking at 2 dice, and I did define these as 2 six-sided dice, and I'm looking for the 2 dice to add up or sum to equal 7. My question on the previous screen said I needed to repeat this process 10 times. So I'm going to simulate rolling the dice 10 total times, and I'm going to count up how many times in those 10 different rolls will I get a sum of 7. And it looks like we're getting pretty good results here. So we rolled the dice a total of 10 times, and 4 of those times resulted in a sum of 7. So we got 4 out of 10 rolls, or 40%, or 0.4 of our experiment resulted in a sum of 7. When we perform our experiment, that's going to be this, that is the empirical method that we're talking about from above, empirical method. Anytime you perform an experiment, you're performing an empirical method of finding probability. Now, you might be asking yourself or wondering if the math or theoretical tells me that I'm supposed to get a rolling a 7 from 2 dice approximately 17% of the time. How come when I did it just now using the empirical method or using an experiment, it happened 40% of the time? Well, remember, we opened up our idea about probability as being what we expect to happen in the long run. We only rolled the dice 10 times using our empirical or our experiment here. So 10 different experiments resulted in an outcome of 40%. But if we were to keep doing that over a very long period of time, again, maybe 1,000 total times, ultimately we would get close to our theoretical model, which is at a 0.167, or rounding up, we would be at about 17%. Now, let's do this same thing, only let's talk about the probability of rolling snake eyes. And we'll just do it using the theoretical method. Now, snake eyes, if you're rolling 2 dice, snake eyes occur when we have the 2 dice and they land on ones each, on a 1 each, so because they look like eyes. So the probability of rolling snake eyes says we have 36, again, possible combinations for outcomes, but there's only one way for me to roll a snake eye. So changing that to a decimal, I'm going to take this to 0.028. So the theoretical or classical method for calculating probability in that case tells me that the probability of rolling a snake eyes would occur in approximately 0.028. Now, how do I define, or not define, how do I interpret my probabilities? In order to interpret these probabilities, let's start with the one we just completed, the snake eyes. I'm going to come over here and I'm going to underline the last digit of our calculation, which is an 8. And if I look at that, I want to understand that that 8 is in the thousandths place of this number. So the 8 is in the thousandths place. That's going to help me to interpret my probability. To interpret this probability, we would say that in 1,000 different rolls of a pair of dice, we expect 28 of them to result in snake eyes. So let me say that again. In 1,000 rolls of a pair of dice, we expect 28 of them to result in snake eyes. Now, does that mean that exactly 28 out of 1,000 will result in snake eyes? No, it's just what we expect to happen. There's going to be, sometimes it makes it, sometimes it doesn't, but in the long run, we're going to get close. Let's interpret our previous probability, and I'm actually going to change my probability here for rolling a 7, and I'm going to take it down to 0.17. So we're just going to take it to 2 decimal places instead of 3 for this example. If I look at that 7 here, the 7 is now in the hundredths place. So to interpret that probability, we would say that in 100 rolls of a pair of dice, we would expect 17 of them to result in a sum of 7. Again, when we use a math formula, that's considered the theoretical or classical method of finding probability. And anytime we perform an experiment, that's considered an empirical method for finding probability.